Okay, so today we're going to be looking at uh, arithmetic sequences in our discrete functions unit. So first, let's talk about what a discrete function is. So we've been working with functions with all this time. Usually we have some sort of x value for a function. Discrete functions, we usually use the letter n instead of the letter x. Now the letter isn't super important, but the reason we use n is because with discrete functions, instead of having a continuous series of values we could have, like 1, 1.2, 1.317, we could have all sorts of decimals and stuff. With discrete functions, we have very distinct separate values we can have. So our inputs, instead of being any real number, are only 1, 2, 3, 4, 5. They're discrete, specific whole numbers. So a discrete function is a function that is made of separate, not connected points. Okay. So if we look at some of these examples we'll look at in a little bit, we can see that we have a list of distinct separate points. And there aren't value, if this is the first value and this is the second value, there's no like value 1.5 like in between. Okay. And these things below here are sequences. And a sequence, this is a bit of a longer definition, it's just a set of numbers usually numbers, terms, or items. We'll almost exclusively work with numbers. Usually separated by commas. Arranged in an order. That can be identified by a pattern or a rule. So it's a list of numbers, but they're in a specific order, and that order is determined by either some sort of pattern or some sort of rule. So maybe if you look at those two lists we have down below, you might be able to see that there is a pattern connecting all those numbers. And we'll talk about what that pattern is in a little bit. Okay. One last definition here is arithmetic sequence. So arithmetic is a specific type of sequence. Okay. So arithmetic sequences are sequences with a constant difference. So that's a plus or minus difference. Okay, so from one term to the next, we're always adding something or subtracting something between terms, a constant difference between terms. Okay, so let's take a look at these two examples. Example sequences, arithmetic sequences, in fact, and let's identify their difference, and we'll kind of talk about them a little bit. So This first one goes 14, 11, 8, 5, 2, and then dot, dot, dot. It keeps going. And we may notice that there's a difference between each one, right? So it goes minus 3, minus 3, minus 3, minus 3, and presumably would continue that pattern, right? So minus 3, and then down 3. So it's going down 3 each time. So the difference is that. And we can label these terms. So they're distinct terms. So this we would label as T1 for term 1. This is T2 for term 2, T3 for term 3, etc. And you'll notice that there's no term 1.5. That's what makes it discrete, that there's only specific terms, term 1, term 2, term 3. For example, we've talked a little bit about discrete before. When we talk about, say, populations of people or of animals, we always talk in discrete terms. You can't have half of a cow, at least not a half of a living cow. So we can't have half terms. There's nothing between these. It's term 1, term 2, term 3, no term 1.5 or anything like that. Okay, if we look at the second one, it has all these distinct terms again. And we have a different starting point. So this one started at 14, this one starts at -3, and this one's up to -1, up to 1, up to 3. And if we look, it looks like it's a constant difference of add 2, plus 2. And then from that one to that one, plus 2, dot, dot, dot. So every term is 2 greater. And that's what makes them arithmetic sequences, is the pattern is a constant difference of plus or minus something. All right. So to work with these sequences, we'll do a couple things. Mostly today we'll be doing like predictions. So like what is the 20th term or something like that. And of course, we could just write out all the numbers, but that only works so well. So we want a method to be able to say, like, if I want term 1,000,001, I don't want to write out 1,000,001 terms. I would like there to be some sort of equation where I can just say what term number I want, and it'll tell me what the value is. So this is what that equation looks like. T, and then it's got a subscript n, which is just these like little labels like the 1, 2, 3, equals a plus, in brackets, n minus 1 times d. Okay, so Tn, we'll just write down what each of these kind of letters or positions represents. So Tn is the value of term number n. So for example, term 1 is 14 in this sequence up here. Term 3 is 8. A is the value of the first term. So for our above sequences, A would be 14 for this sequence, and for this other sequence, it would be -3. So it's just the value of that first term. N is the term number itself. And you'll notice n shows up twice. It shows up as the label for our term, and it shows up in our equation as well. Now this t subscript n is very commonly used in discrete functions, but it is very similar to f of x, right? This is like a tied together notation. And the n is just a label that we're filling in. Okay. D is that constant difference. Okay, so the constant difference for this first example was -3. And for the second one was +2. So that would go in our equation. And we can kind of see how this equation works. So it's the first term plus the difference multiplied by how many terms away we are, right? So 1 minus, if we looked at term 1, well, it's just going to be a. And if we plugged 1 in here, then we get a 0. And the difference doesn't apply any times. But if we looked at terms, say, like a million, then we'd multiply the difference by 999,999 and add that to the first term. Okay, so let's try an example. So here's our sequence. It's the same one we did up here. And we are going to try to find term 27. So let's just write down the things we know. So we know n for the thing we're trying to find is 27. We know a, remember, is the first term. It's 14. D, that's our constant difference. So we found that to be -3. It's going down by 3 each time. Okay. If you're ever doing one of these and it's not constant, so it goes like -3, -3, -2, -2, something like that, then that would not be an arithmetic sequence. Arithmetic sequences always have a constant difference. If it ever changes, not arithmetic, which means we can't use the formula we just learned. So let's try to find T27 using our equation. So T27 is going to be A, 14, plus n minus 1, 27 minus 1, times D, -3. So the difference applies 26 times because there's a separation of 26 terms between the first and the 27th. So we multiply that together, and 14 plus whatever this multiplication is, and if you punch it in your calculator, you get -64. Right? So we could think, oh, these numbers are going lower. The next number would already be -1, and if we kept going, by the time we get to 27, we get all the way down to -64. Okay, so let's try something a little bit different. And this one's connected to a concept we learned in grade 10 called linear systems, solving linear systems. So you'll notice that this equation is very similar to the equation for a line. Right? So it has some constant difference, kind of like the slope. This is kind of like your y-intercept, not quite the same. This is kind of like your x value. It's similar. Okay, but let's see how that works out. So here it says an arithmetic sequence has T7 is 13 and T14 is 34. Find the first term, then find the 27th term. Okay, so we don't know what A is. That's what it's asking us to find, the first term. We don't know what the difference is either. All we know are two different terms, but we know what the n value is for both of these terms. So when n is 7, the value is 13. For term number 14, when n is 14, the value is 34. So what we'll do is we'll write that out. So for T14, let's write out what we know. We know that 34, the value of the term, is equal to A, we don't know, plus n minus 1. So n minus 1 is going to be 13 times the D value, whatever D is. Right? So we don't know what A and D are, but we know this about term 14. And we can also write out what we know about term 6. And you might be thinking, oh, Mr. Battering's writing this kind of weird. You'll see why in a moment. So we know that the value, oh, I wrote T6, but it should be T7. T7 is 13. It's the value of the term. We don't know what A is, but we know that n minus 1 will be 6 times D. Right? So here we could write out 14 minus 1, and we could write out 7 minus 1. I'm just doing the subtraction in our heads. It's going to make the next step a little cleaner, that we're nice and organized. Okay. So because these are from the same sequence, the A values, like the first term is the first term, right? So these are the same. And the constant difference is constant, so the D has to be the same. So here we have two equations with two unknowns, and we can use substitution and elimination to solve. So we can try that. So I think subtracting these two equations might work well. So if I subtract these, Let's see what happens. So we do 34 minus 13, 21. A minus A, well, that's just 0. 13D minus 60 is 7D. And now I've eliminated the A's, and I can rearrange this to solve for D. So I just have to divide both sides by 7. So we get 21 over 7 equals D. Well, and that's just 3. So we can, let me just extend this down. So we get D is 3. Okay, so that is our constant difference between each term is 3. Okay, we still don't know what the first term is. We still don't know what the 27th term is. But now that we know the constant difference, the D value, I can plug that into either of these original equations, and I can then solve for A. So I'll plug it into the bottom one. It's got smaller numbers. I think that might be a little easier, but it doesn't make a difference. You'll get the same A value no matter what. So I'll plug it into this bottom one. So I got 13 equals A plus 6 times 3. Just noting here that we're plugging this in there. The D value that we now know, we plug into the equation to solve for A. So that's going to be 13 is A plus 18. So I'll subtract 13 minus 18 is, our A value is negative 5. And that's the value. Remember, A is the value of the first term. So for the first term, here, we'll just write it up here, negative 5. Okay, and now that I know A and D, I can find any term, the value of any term. So I want T27. So we can write term 27 is equal to A, use our general equation, plus n minus 1. That's just going to be 26, but I'll write out the full thing, times D, 3. And we can punch it in our calculator, or you can write that out if you would like. Do the multiplication, that is subtraction, and we get 73 for term 27. I'll just circle that as an answer. So term 27 is 73. Okay, that is it for arithmetic sequences.